I hope you guys can see my screen as far as it's got that watershed approach to restoring the Little Plover River. And I'm sure a lot of you guys have heard and or seen enough about parts of this project in the past. The Wisconsin Wetland Association had a bunch of sessions, and there's already been one here. So this is getting a lot of good coverage. There's a lot of good work that's done with the mitigation bank work and so forth. I guess this was a local-led approach, but yet there were a lot of collaborators and partners to get something like this done. So this is just a few of them here. Okay, oh, too fast. This is, I guess, a picture of the watershed. It's a small river in the middle of Portage County. You can see Stevens Point over here. Then the eastern part of this watershed, I don't know if you can see my mouse kind of going across the screen, most of that is a closed depression, and therefore it doesn't really impact surface water. We've got a fair amount of that in Portage County. So the Little Plover River starts, the headwaters are in this area. You can see the red circle where most of the work was done for this part of the project.
Dan, I'm sorry to interrupt, but we're seeing your PowerPoint, like your software and not the presentation screen. It's fine if you can't switch monitors, but you might just need to reshare.
I'll do that, try and do that now. Does that help?
I see somebody in a boat.
Oh, no, that's not it. Then I got to do something different. Okay.
Well, we can see it fine. Oh, Tracy, can you?
That. Yep. And that should work better.
Look at that.
There you go.
Now it should be the full screen.
Thank you, Dan. That looks great.
Sorry about that. Multiple screens confused me there. I hadn't done a presentation when I've got this many screens. Okay, so let's get back to where I was. So this is the area that was in that little circle. You can see the field that we basically made into a wetland. The higher points, as you'll see, were some of the drier soils. You can also see some of the soils that were hydric in nature. You get an idea of the 3,600 feet of ditch that was filled. You can also see here the Little Plover River, the natural channel, kind of ran through the woods here. Most of that flow was diverted to this ditch. So again, there were lots of parts to this project, and in hopes to slow the flashiness, look at, again, raising the groundwater levels, and restore some of the natural stream features in the watershed. There were two parts to this. The main one, obviously, was the ditch fill. To create the ditch fill, we obviously had to find some material. Well, that was the part of the restoration work that was done with the wetlands. So two large scrapes were created to basically come up with the fill to complete the ditch fill. This is the plan view of the drawing done by Montgomery Associates. There were numerous hydrological and ecological engineers that were also collaborating and parts of this project. A lot of monitoring went in with different monitoring wells. As many of you know that are currently involved with mitigation projects, there's a lot of monitoring wells and different monitoring things going on right now as well. You can see over here the big area on the left, which was scraped out. And if you remember the aerial photo, that was kind of that higher dry spot. The same thing on the eastern half of this. And again, you see the roughly 3,600 feet of ditch that was filled in. These are just some pictures of what the site looked like before. You get a real good idea of the ditch here. It was approximately 6 feet deep. The top width was somewhere between 15 and 20 feet. Again, it was an irrigated field. This is a picture showing the cover crop that was planted after the 2018 harvest. Again, some further photos. The main photo here shows the center ditch. Again, you get an idea of the groundwater impacts here. These photos were taken in 2019, and as many of you are aware, we, as well as a lot of other counties, are dealing with very high groundwater issues. So I'll get into some of the complications that were caused because of those issues. The project started basically in that southwest corner with a sediment barrier. Most of us have put these into some type. This is just basically a rock riprap, 2 foot high, roughly sediment barrier to let the water continue to flow through and trap the sediment behind it. One of the big discussion points and was whether or not to leave some of the vegetation in the ditch. There were little or no compaction standards we needed to adhere to here. So some of the NRCS compaction regulations and that type of thing were not needed to be followed. So that material was left in there along with all of the sediment that had deposited over the years as well, which in turn you'll see created some issues. So we started out with removing the bigger trees from the ditch itself and the ditch bank. The excavator did that while the dozers were basically creating windrows in these large areas. They pushed the topsoil one direction and then pushed the sand, which was predominantly the big part of the fill, in the windrows in the middle so they could push the black dirt back into the wetland areas. Then once those windrows were done, the hauling started. It was all done with off-road trucks. The dozers, gradually pushed it into the ditch. As we could, the haul trucks were used to compact to the best possible, I guess, based upon, their loading and unloading methods and the different scrapes that were used as far as to ease the hauling distances as well. To get into some of the obstacles, again, groundwater, as a lot of us are aware, was really high. And most of the pre-monitoring was done prior to some of the peaks. So once the construction started, we had almost 8 to 10 inches of rain during that month-long construction period. So we started construction in the northeast part of that ditch and created that the east swale and the east scrape first, started hauling that material in, which in turn then forced the water to run into the natural channel, but it also backed it up. Part of this material from the original ditch digging that was done decades ago created a mound, which we knew was there based upon the surveys and so forth. So we had to remove some of that, kind of create a weir for it to get to the natural channel. But during the scrape creation, we got down to groundwater level. We assumed it was probably going to be a little deeper than it was. But again, due to the levels being so high, we actually hit it within a couple of feet. Thus, the water wanted to flow, stay in the scrape, which made it really hard to create. So we had to divert the water. So there were lots of things done on the fly here, which was primarily after the survey. The county's main role was on-site stuff. So it was a lot of consulting with the engineering firms and those consultants to make sure we were meeting the design requirements as well as the environmental requirements here set forth by the DNR and Army Corps. So what we did with some of that high groundwater in the east swale and east scrape was to actually run it back to the ditch to the north. This was originally supposed to be an inlet to deal with high water flows for some of the flood routing, to get the water from the ditch into the scrape to enhance that wetland. Little did we know that the water was so high it would actually run out. So we'll be curious to see when water, if it ever gets this high again, to run into the scrape and how this is all going to work together and kind of balance itself out. Then once we got mostly done with the east side of the scrape, we threw in the sediment or the armoring, the riprap along the bank where it was almost a 90-degree corner to route it back to the natural channel. So we removed the original berm that was there and created a rock weir, and basically rock riprap that slope so that would kind of tumble over that. So you can kind of look upstream with the slide on the picture on the left. That's looking up the ditch in that northeast corner. This is an aerial view of that corner. You'll get a real good idea from this drone picture, the kind of groundwater issues we were dealing with. And you'll see in some previous photos as well, how the water dropped in the last year. So a lot of this construction was done in mud, which complicated things dramatically. This is a nice view because this shows the 2020 photo, and you can see looking down on that, again, the angle, the weir that was created to dump it back to the natural channel. And it does show you as well how the water table did drop in that less than 1 year time period. This was the weir, the original berm from some of the fill. Again, if you can see my mouse was right in that area. So that berm was broken here or breached. So the water would, in a sense, get back to this natural, real braided channel. And again, in hopes of restoring the natural stream flow and that nice habitat. This gives you an idea where that angle and where the riprap and that rock was placed. This is just another neat aerial view of the inlet, which in turn temporarily was our outlet back to the ditch. We didn't riprap or feel we needed to stabilize that. We were, again, hoping that natural vegetation would get in there rather quickly. We didn't anticipate having all this water table issues. So currently that is now vegetated and looks quite nice once the groundwater receded. Again, because of all the groundwater issues and the inflow and outflow from our scrape, just due to the high water table, we had to, again, create a secondary outlet on the fly. We anticipated, based upon the flow volumes and so forth, according to the engineering calcs done by the consultants, that the water should flow into the natural channel. Well, again, with the high groundwater levels and everything that was occurring, we had a lot of water running everywhere. So down in the southeast corner, you can see where that star is, where we had to throw this secondary outlet as part of this. A big part of these soils, there's real sandy. So we have really high infiltration rates here. So when you're calculating your runoff numbers and all of this stuff, it's hard to base it on what's currently there when we're not dealing with frozen conditions and or groundwater levels that were so high that inhibited those infiltration rates. So now we basically got some drone pictures of that southeast corner where the secondary outlet was placed. Again, you can see the water issues that we were dealing with during construction, because this was after this was all done. The drone pictures were taken at that time. This is looking northeast, up the swale which enters into the east scrape. You can also kind of see in the middle photo here where the riprap was where the berm was breached and the weir was placed to dump it into the natural channel. Again, this area is all revegetated, and there's a huge revegetation plan and monitoring that is all part of this and ongoing now. This is just another view of further north. You kind of see the line where the irrigation rig ends. That currently is a veggie production field, which was very similar to the field we did this construction in. And the hopes is maybe in the future to work with this landowner. It's the same landowner again, and kind of continue this project north. But that's yet to be determined, and I guess we'll see how all the groundwater aspects are impacted by the current project. This is another close-up view, I guess, to kind of explain further some of the issues and how we had to kind of address them on the fly, which I know a lot of us are used to dealing with as far as construction goes. Right in here, you'll see, again, after we placed the secondary inlet, the water started to recede, but because we didn't have certain compaction standards within the ditch, we had differential settling throughout it, which the hope was to kind of create a hummocky, varied wetland habitat, which is a good thing. But in this case, we had water leaving in certain areas. So we had to go back in and place additional fill on top of that. The original plan was to call for filling the ditch in excess of 1 feet above the native ground. And obviously with the settling and the different settlements, that wasn't quite enough in that location. This is an aerial view. If you remember the black slime that we had in the one slide that we had to deal with, again, because we did not remove the material from the bottom, that obviously rose to the top as we pushed the fill in. And what you ended up doing, we didn't want to overload the sediment barrier. And the assumption was that was going to top when we got close to that, which would in turn dump all of this right into the ditch and downstream into the rest of Little Plover River. So we actually kind of filled the middle portion of the ditch to kind of create a huge dam, which in turn then created all of that sediment being deposited on top. And then we got all the rain. So it was a mess. We had dozers stuck and all sorts of different issues that occurred. We had to do different pumpings and work with the DNR to make sure we were pumping that to, in a sense, the right areas to get, again, the sediment to settle out. So we had to create, additional smaller berms and or pools, settling pools to allow that. So this shows one of those areas where the previous slide had all of that, how we spread that out across the middle portion of the ditch. This is looking from the north end, again, looking south. You can see the western scrape. The area that is right in the forefront of the photo shows where we created one of our settling pools and areas that we had to kind of, again, do on the fly where the water was pumped to. This also shows well how we tried to get not a uniform bottom. Again, this is wetland habitat, and we wanted to have in a sense, the contractor left his laser grade equipment off and, try and create that undulating bottom when he respread the topsoil throughout these scrapes. This is, again, looking in the opposite direction, back to the north. You can see the silt fence, which we had to install. Again, we didn't anticipate this being an issue, but again, because of the high groundwater and how we had to modify on the fly and with the different sediment pools and so forth, this became a reality. So that had to be installed. So that ran across the whole western side of the property, protecting that ditch, which is again next to the road, which you can kind of catch a little bit of the road right in here. Hope you can kind of see that silt fence that was put in. Oh, let's go back to that. I guess the key thing here is all of this property slopes from north to south. It's a very flat field. There is approximately 3 feet of fall. So across that whole field, while it looks flat, so that's where the depth came in. We removed 2 to 3 feet in each one of these scrapes. Some places end up being a little deeper, obviously, because we were doing this in water, so it was hard to get exact depths. But again, that varying type of habitat was key in what was, I guess, hoped to be part of the mitigation. This is at the outlet down in the southwest corner. Again, we had to rock riprap that in case we had overflow, which wasn't always necessarily anticipated as part of the design, but seeing the reality of the world and how things work when groundwaters hit record highs, things are greatly impacted. So we riprap that, keyed that all in, and that was one of the last parts that we did. We were able to use a lot of the stone from the sediment barrier in this. This shows again an aerial view of that with the 2020 photo. You can see the rock in that corner, and then again how the two ditches used to come together. The ditch that was filled is obviously in here, and this is the ditch that ran along the road between the field. There's our silt fence still, and this will continue obviously down to the navigable or the original native part of the Little Plover River. Again, this gives you an idea where it was in relationship to the whole scale. And this is kind of one of my favorite photos. It looks at, it's a 2020 flight again. So you can see the areas where we worked and kind of how we made things. Again, here's our outlet. All of this ditch was filled. This is that middle portion which was filled. You can still see some of the black slime that was left there, that sediment deposit. And this is approximately where we did that kind of secondary fill, the backfill against where we stopped right in here. So it gives you an idea of what we were occurring with and what we were dealing with. So we stopped it. We did a plug in here. We allowed that sediment to flow out over the top of the ditch and deposit in this area before we finished this fill in here. This also shows, again, where we ended it. And this photo really shows how the natural channel has already improved. Due to some of the ongoing monitoring, we know that the groundwater levels have already increased approximately a foot. And we've got our flood routing in. Obviously, we don't need that now. We're relatively dry here based upon a lack of snow this winter. But this is where that passage is, in a sense, to mitigate the flashiness and the flood routing into our scrape. It also shows, again, how the bottom was done at various depths. And this shows the comparison again of the 2015 pre-photo and the 2020 photo. So you can again see how we mitigated that. We left the areas that were hydric in nature, and it shows up quite well. So you can, I guess, kind of compare the two as far as it goes and see why the engineers and the staff did the project in relationship to the natural ground that was there and the natural features. This also shows quite well the original natural Little Plover River doesn't show up real well, and suddenly we've got a dramatic increase in flow in that natural channel, which was one of the biggest reasons to address this. So that's basically all I have. If there's any other questions.
All right, great. Thanks, Dan. Yeah, we got about 5 minutes or so. If anybody has any questions.
I have not seen anything in the chat yet, guys.
Well, that'll make it easy on me then.
Don't let them off the hook here, folks.
Again, this was, I know we've seen a fair amount about this project. There were a lot of collaborators and a lot of information out there in regards to this plan. I know we'll be discussing this probably further as we look into the mitigation and how successful that is, and or with the different vegetation types and all of those requirements. I believe Josh presented on this yesterday with the mitigation bank part of the conference.
I got a question in the chat for you, Dan. How do you think it would have been different in a drought?
Dramatically. If we would have done this in 2012, basically prior to probably 2016, we would not have hit water in our scrapes. The water out here is somewhere between 7 and 10 feet generally. So again, with all the precipitation and these storm events we've been having, as you all know, the groundwater table rose significantly, which in turn created the problems. The hydric soils are here. Some of it is just the nature of the compaction of the equipment and the fields, and the again fluctuation in the groundwater levels that create that. So it would have been significantly different, simply put.
So got a lot of good feedback from your project, Dan, but I don't think there are any other questions in the chat. Just saying that you had a great project and they liked your presentation.
Okay. Well, Dan, you're going to stick around, I assume, right? For the
Yes, sir.
Okay, so if somebody does think of something, Dan will be available later. But yeah, I think if there's nothing, we'll keep going because we do have 2 additional presenters to get to yet. So next up, we're going to have Wes Kotila with Outagamie County. And Wes is going to talk about a constructed wetland that he had worked on. So Wes, if you're ready, it's all you.
Can you hear me?
Loud and clear, Wes.
Perfect. So as Travis said, my name is Wes Kotila, technician with Outagamie County. I think in the description, we were saying that we were going to be talking about constructed wetlands, but we've kind of changed the name a little bit to an acronym of ARTS, which is Agriculture Runoff Treatment Systems. This kind of avoids that wetland word. Wetlands are great, but they also come with certain, expectations regarding plant life and then maybe future regulations. So the point of these systems is essentially to slow the water down, trap sediment and the nutrients attached to that sediment. So they have wetland characteristics, but are not traditional wetlands. So with that, I'm going to go over some background information about our project area, the planning and design process, and some construction, and then highlight some of the projects we've done in the past 5 years. So for you who don't know, this is our project area. It's Plum and Kankapot Creek watersheds, which are tributaries to the Fox River. The main portions of these watersheds are near Kaukauna, which is between Appleton and Green Bay. So why install these systems? There's been a major loss of wetlands and natural areas throughout the watersheds that we work in, which is nothing new for most of you to hear. With this, there's less storage and water runs off the landscape at a lot faster pace, leading to high peak flows and high erosion as seen in the picture on the left. Along with this erosion, the loss of these natural areas has led to a change in habitat for wildlife. So adding these structures can actually help start to be the source of both of these, or help cure both of these problems. If any of you listened to Jeremy Freund's presentation yesterday afternoon, you'll recognize the map on the right. This type of mapping analysis is something that Sarah Cuso from our office has been developing through GIS. A very brief description of it is that the analysis calculates both the pre-settlement flow rates and the current land use rates for all the water or sub-watersheds shown. The difference between those flow rates is then used to calculate the storage volume needed to return to those pre-settlement flow rate conditions, which in theory should reduce the amount of peak flows and erosion happening on our stream banks. So the map on the right shows the acreage needed in each sub-watershed to store a 2-year rainfall event. So by adding in the number of acres shown, the sub-watershed would theoretically be able to hold enough water to release at that pre-settlement flow rate. Typical planning for these projects can be some of the most time-consuming aspects, as a lot of you know. So just make sure to be checking mapping such as hydric soils and floodplain. And depending on where you land, you could have permitting through local zoning, DNR, Army Corps, etc. We also take into account location for the project. We try to target areas that rank highly on the mapping that Sarah's been doing, along with looking at the potentially restorable wetland layers Nature Conservancy has been putting together. Another thing that is very helpful in design and planning is the Presto mapping software that DNR uses or has on their website. Essentially, you can click on a section of whatever stream you're working on, and it delineates a watershed for you. The software also breaks apart the watershed into land use and gives some background information on the stream itself. The report looks similar to the picture on the left there. That can be really helpful with your like TR55 and that kind of stuff as well. So our typical ARTS design combines aspects from NRCS sediment basin standard, the constructed wetland standard, and urban stormwater techniques. We target a release rate of the treatment area of 5 to 7 days. This helps to promote wetland plant growth and also maximize the sediment and nutrient retention. For us, we're targeting 80% sediment retention and 40% phosphorus retention within these systems. The other thing about these designs is that each one is unique. There's no real magic bullet to the design process. So depending on your site location, size, and other characteristics, different strategies are utilized. But the main concept is to slow the water and retain those sediment and nutrients. HydroCAD analysis is a major aspect of the design. So for those who have not used it, HydroCAD is a relatively simple software that can model flood routing for different types of projects. This slide just shows some of the pieces of the software. Essentially, you can create all your sub-watersheds and route them into your pond or basin. You can then model any outlet structures that your site may have. And after your site is set up, you can then route specific size storms through the system. So the software can load in storm sizes for specific counties as well. And then you can run the software and it'll tell you if your basin can safely route the water. And it also spits out the hydrographs as seen on the right. So the red arrow is your inflow and the green arrow is pointing at the outflow after your system is in place. So as you can see, no more peak flow, which is a good thing. So typically we use this software to model the meadow hydrology for the site, which is essentially the pre-settlement conditions. And then we compare that to what is on site now. And the difference is the amount of storage that we would need to get back to those pre-settlement conditions and theoretically less erosion. So I'm going to highlight some of the projects that we worked on now. This is the first site that we installed outside of Kaukauna in 2016. There's surface water and tile runoff that are both being monitored by USGS. And I will discuss some of the monitoring data in a few slides. Relatively simple design. The water runs into a sediment basin and then flows through 2 wetland cells separated by a rock spreader bar, which you'll see on most of the other sites as well. This is from the vegetative treatment standard. The land out of production on this one was also very low, which is great for a selling point to farmers and landowners. And also with this one, even the land that they did take out, we designed the berms to be farmed on the outside just in case they wanted that space back. But for this site, the farmers stayed away from them, which has been nice for us for access to the site. So when the project was initially installed, there was a wetland planting concept that would have cost more than the construction of the basin itself. So to limit cost, we decided to go with a slightly different approach of essentially just seeing what would grow from the native topsoil, which had some good things and some bad things that I'll touch on after a few more slides here. So for design, the treatment area is about 0.5 acres, which is 5% of the 10-acre watershed. This comes from urban stormwater. Again, you can see the hydrograph that was developed in HydroCAD. So with this, we showed that the system could safely route events all the way through the 100-year event while slowly releasing that last 18 inches of water for 5 to 7 days. The final cost was around $12,000 due to the relatively simple design and size. There's some maintenance involved with these systems, and they're very similar for all the systems, so I probably won't mention maintenance again. But in this case, there's a yearly mowing by the landowner just to keep that vegetation controlled and to prevent woody vegetation from establishing on those side slopes and whatnot. The other major problem that can happen for projects like this is muskrats. They burrow into berms and side slopes and can cause leaks and other problems. There have been a lot in our basins. Luckily, they haven't caused too many problems so far. But one interesting thing I heard in a webinar earlier this year was that one mating pair of muskrats in the spring can turn into something like 140 by the end of the year. I don't know how much I believe of that, but it's if you see muskrats, there's more to come. So as I mentioned before, we kind of went with the native topsoil approach for our vegetation. So predominantly here we've had narrowleaf cattail, which is not exactly a sought after wetland plant, but it seems to do a good job of taking up phosphorus, which is what we want for these systems. 2 falls ago, we went through and cut down all the cattails and then rake them all out of the complex itself, which wasn't exactly a fun process. But UWGB was able to take the samples of the plants that we raked out. They dried them out and measured the phosphorus that they were holding, and they estimated that we removed almost 2 pounds of phosphorus just by removing this vegetation. So I said we'd be talking about some monitoring results. This is some of the monitoring results for the site since 2017. The grant is actually concluding now, so there will be a report on 2 of the systems that I'm talking about coming out soon in the future. The red box is showing total phosphorus in and total phosphorus out in pounds. And this is where you'll see that getting 2 pounds of phosphorus in that vegetation is also quite impressive, saying that, you know, there's 18 pounds coming in and only 4 going out typically for most of these years. The blue box is showing the suspended sediment in and out in tons, and you'll see for almost everything, the amount going out is much lower than the amount going in. This is another way to look at the data, the reduction data. First thing I want to point out is the red box is showing the totals from the 3 years of results. And you can see that we met our design goals of 80% of that suspended or total suspended solids or sediment reduction and 40% phosphorus reduction. The next thing I want to touch on is in 2017 and 18, we had major total phosphorus reductions, but we noticed a large decrease in that phosphorus reduction when the upstream field switched from corn to alfalfa. So we have a few thoughts on why that might be. We're assuming that the size of the sediment coming off the alfalfa field is much smaller. So with that smaller sediment size, we need a longer retention period to settle those particles out. And our 5 to 7 day drawdown period just might not be long enough to really get that sediment, those fine sediments and phosphorus to fall out of solution there. The other thing that I'm sure you noticed are the dissolved phosphorus rates reductions. They're not reductions. They're actually higher leaving the site in 2 of the years than entering it. This could be from a few things. The plants themselves that take up the dissolved P eventually die and maybe releasing it back into the system as they sit on the bottom of the wetland. Another thing that I recently learned is that some sites in Canada have noticed that on constructed wetlands where the native topsoil is used, they're seeing massive spikes of dissolved phosphorus leaving the system. The native topsoil can be really high in legacy phosphorus, and then that can actually leach back into the system. So we're looking for solutions for this, and one solution that we're looking at trying out on a couple of our sites are zeolite and biochar filters. And these filters can actually be put on the outlet structure and bind the dissolved phosphorus to the filter. And then when the filters are full, they can be interchanged. So the zeolite filter is something UW Milwaukee's working on, and the biochar is UW Platteville and UWGB in conjunction.
Hey Wes, can you go back to that for a second?
Yeah.
Do you have any idea why 2018 you did have a reduction for your phosphorus and you didn't in the other 2 years?
Yeah, so my thoughts on that are actually, so 2017 was like the first year we didn't have a lot of plant growth. 2018 is when we saw a lot of the plant growth take off. And we probably had a lot of, you know, that dissolved P getting taken up by the plants itself. Then when all that plant growth died and there wasn't as much of the new plants coming in, I think that might be why we're seeing kind of a back and forth of those things. I don't know that for sure, but that's kind of my thoughts on it at least. So this is our second site with Heart of the Valley Metropolitan Sewerage District. This site was part of the first water quality trade for sediment in the state. Instead of initially making changes at their facility, they were able to pay for installation of different conservation practices throughout the watershed. And then they had to monitor it and prove that it was working and whatnot. So this site is also being monitored by USGS. This is a before construction photo and then a during construction photo. You'll see that we're also working in a kind of natural waterway, so we're not taking as much land out of production.
Wes, I got a question in the chat if this is all right time.
Yeah, I'll just take questions at the end now, okay. Just because I don't know exactly how long I'm gonna go. I don't want to take up any of Luke's time.
That's fine. Sounds good.
Okay. So this is a site or a picture of the site after about 2 years of being in production. And this is a kind of visual breakdown of how the site is working. The runoff goes through the USGS monitoring flume and into the system through a rock spillway, and then enters our first sediment basin, which is acting as our primary sediment catchment. After that, it goes through 2 small wetland cells before getting into another sediment trap, which acts as kind of like a polishing station before leaving the site. So very similar to our first site, just a larger watershed, and then we added in that second sediment basin. This is a plan view of the project. There were 2 tile lines originally that went through the site. Typically, we would route both of those lines into the system, but due to the USGS monitoring and needing total containment, we would have had to set up a whole nother monitoring station on that second tile line, which would have added cost and complication. So the tile line was instead routed around the system. But after the monitoring is complete, it's something we may look at, routing back into the system. Again, the overall design was very similar to our first site. This one had a 21-acre watershed, which 17 of it was ag land and 4 acres of it were urban runoff. Again, using our 5% rule, that brings us to about 1 acre of treatment area. That acre is split between sediment basin and wetland areas. We used the surface area equation from the sediment basin standard, which is shown here on the slide, to determine how much square footage of sediment basin we needed. So our Q out was determined using HydroCAD, and we used the settling velocity for clay particles to determine that surface area for the sediment basin. We don't have a lot of monitoring data to show for this site yet, but we should have it soon. The preliminary data that we do have is showing that we aren't quite getting that 70 to 80% reductions that we were hoping for. We think this is possibly due to the contributing watershed being in alfalfa for the first 2 years of installation. And then this past year, the land actually went into corn, so we're interested to start seeing the data that we're getting off of that. One interesting thing that we did kind of find out with the monitoring was that there was some massive spikes of phosphorus loading after a few storm events a couple summers ago. And we were kind of confused on why this was happening. But after talking with our contacts at USGS, we were able to narrow down what probably happened. So the monitoring equipment has cameras on it. And they were able to look back and see what the farmer on the contributing land was doing a couple weeks before. And they had actually been applying liquid manure to their alfalfa, which is a practice that in the past has been suggested to farmers. So if we're still getting this much phosphorus leaving the field after 2 weeks, this might be something we might want to look at as not the right solution. But the good thing is that instead of this massive spike going directly into the waterway and eventually into Plum Creek, it was captured in this basin itself. So we're looking at these as possible solutions for manure spills, possibly if we can get these set up on the edges of fields, and the farmer has a outlet control where they can actually shut off the outlet. We could contain some of those problems that we're having with manure. This site, we've actually had a much more diverse population of wetland plants. Several different sedges and grasses have shown up, all sorts of bugs and birds and whatnot. And we also discovered that there's quite the fish population in that first sediment basin, which is kind of cool and unexpected. So this is our third site. It was actually designed by Jan Hosper from Brown County. And then we asked him to add in the little constructed wetland basin at the bottom of the hill there. So this site was much different from the first two, due to the site being in a low-lying area of the field. It's surrounded by steep hills. It was kind of hard for the farmer to actually get anything going down there. And the landowner was planning to turn this area into a buffer zone and adding in those waterways and a wascob in the gullying areas of the field. Instead of doing just the buffer, we proposed to add the small treatment area at the bottom of the slope. So this system basically is designed to route small storms through it, and then the larger storms have overflow areas where they can overflow the system. Again, this kind of shows the wascobs and the waterways contributing to that wetland. So this site, we learned do not install waterways late in fall, no matter what. Our grant was ending, so we tried to force construction super late in fall, which was not a good decision. The waterways blew out several times, and we ended up having to clean out sediment out of the wetland 3 or 4 different times. A whole bunch of other issues, but as of this past fall, I think the site was finally functioning as we wanted it to. The site doesn't have any monitoring, so I don't have any results to talk about there, but the cost was around $29,000 plus the repair bills. So this is our most recent installation, the Vanda Hay complex. The basis of the project was to pull water out of Plum Creek above the ordinary high water mark, route it through the arch system, and then put it back into Plum Creek downstream. We actually mimicked a project from La Crosse called the Halfway Creek Marsh Project, which was finished in the year 2000. We were actually able to meet with some of the key contributors to that project in 2018, and they helped us incorporate some things into our project that they noticed about theirs. So the design for this one is a little bit different, so I'll try to run through it quickly. I developed the Watershed using the NRCS Watershed Creation Tool and ArcGIS, and also ran the Presto report as a comparison. The Watershed is approximately 3,100 acres, so it's slightly different than the previous slide showing 28,000 acres for Halfway Creek. But based on that Watershed, we were able to run the flood frequency spreadsheet to determine approximate storm sizes. Using that in combination with some on-site characteristics, we were able to determine the ordinary high water mark of the stream, which is what we needed to, we needed that elevation in order to determine where we could set our inlet pipe to follow DNR regulations. Another thing that we were kind of lucky with here was that there was an existing HECRAS model that had been developed when the floodplain modeling was done for Plum Creek. And since the cross sections were done so long ago, we modified the cross sections to better represent the site. But what the HECRAS software can do is it models the approximate stream water surface elevation throughout the system for different size storm events. So we had cross sections at our approximate inlet location, halfway through the system, and at the outlet location. So when we would put in different storm sizes, we would get water surface elevations throughout the site. And by doing that, we were able to determine like what size event would actually start water contributing into the system. So for us, it ended up being about 25 CFS that would cause water to start entering the system. And right downstream of this site, there's a USGS monitoring station. So we were actually able to take some real life data and kind of add it back into the system. So we were able to look at past data to determine approximately how many events we should be expecting to enter our complex. We looked at all those peaks that went over 25 CFS and determined that approximately 10 to 12 events should be entering the complex on an annual basis. So with this data, we actually took one of the hydrographs and the sediment and phosphorus data from that hydrograph and approximated the amount of sediment and phosphorus that we could store in each storm event. So this is a picture of math. Try not to read any of the columns, but essentially what we did is we took the details from that storm, did some math involving the flow coming in per hour and the TSS and phosphorus loadings for the storm, converted it to pounds and added it together. So it's not 100% accurate, but it provides an estimate of what we could capture in each event. So if you can see on the bottom, each event could be contributing around 3,100 pounds of sediment and 8 pounds of phosphorus. And I forgot to mention, but the storm we picked was approximately a 1-year storm event, which is what we're kind of targeting for this system, is those smaller storms. So this is an overhead view of the site itself. Pre-construction is on the left and then mid-construction on the right. The water is routed from the upper right to the lower left. So in the upper right corner there, the water enters through an 8-inch agri-drain pipe and then goes through a long rectangular shaped sediment basin in order to get that initial sediment fallout. The basin is approximately 5 feet deep and a ½ acre in size. And this basin allows for about 3 feet of sediment accumulation before it'll need to be cleaned out. The rectangular shape and location helps with ease of trap cleanout for the future. So then the water is routed through 2 wetland cells that are approximately 1 acre in size. This section is intended to be shallow wetlands and is where we hope to get additional nutrient uptake due to the vegetation that's going to establish. And then the last cell is a combination of sediment basin and shallow wetlands for additional sediment accumulation and water quality improvement. So there's a lot of material that needed to come out of site here, 11,000 cubic yards. So instead of trying to move all this stuff or all that material off site, the material was used to create a small hill on the south side of the site there. The pre-existing uplands along with this new hill will actually be planted into a native pollinator mix during this coming spring. So this is the deep pool system at the north end of the project. The contractor that we used had GPS equipment and was able to actually take our CAD file and put it directly into the machine. Made it super easy for construction checks, but still we ran into a few issues. For some reason, the lowest elevation in the wetland wasn't showing up on CAD when it was transferred to an older version. So I went out there with Travis one morning and I was all excited to show off my cool new project. And the first thing that happened was all my elevations were off by about 1 foot, which caused a little bit of a panic, and Travis was laughing at me, but it was a relatively painless and easy fix. But that's just a word of caution for those who have contractors using that GPS equipment that you still need to go and do your checks. So this is the blue area shown here is the approximate flooding area. So it just shows the combination of that shallow wetlands and those deep wetlands. This landowner is very interested in adding additional habitat for ducks and other animals. So he's planning to put up some birdhouses and on the hills and interested in adding additional habitat into the wetland areas. Possibly including woody debris and that kind of stuff. This here's the initial sediment trap. Like I said, long rectangle that's designed to catch most of the sediment for the system. The overall cost on this project was $87,000. So we're seeing somewhere between that $20,000 and $30,000 per acre cost for a system like this. The other thing that I wanted to throw in as something that I think we should be taking into account with these projects is the landowner for this one actually gave up quite a bit of land, gave up almost 8 acres of rented land for this system to be put in, which over a 15-year operation and maintenance plan for the system can actually total almost $17,000 in rental costs that he could have gotten, but he decided to, forego and put in a complex like this for us. So if anything I said doesn't make sense, it's because of these two. We got a puppy at the beginning of the pandemic and then found out we were having a baby. So baby Lucas was born about 2 months ago and he takes away from all my sleeping time. So with that, if there's any questions, I'll take them. I'm also going to show a quick drone video if I have the time.
Yeah, you got about 5 minutes, Wes. So
perfect. Is that showing up well?
Yep.
Perfect. So I can take the questions while this is going. It's basically just going to be showing that second site that I talked about, the Heart of the Valley wetland complex.
Yeah, I think it'd be valuable, Wes, to touch on that one kind of canned question we had talked about with as far as the standards and what standards were followed or didn't or weren't followed, or I think that might be valuable to kind of hear.
Yes. Are you saying like how we could cost share them or how you guys navigated
cost sharing these projects without them fitting into
so we're
standard.
Right. So luckily, Jeremy in our department is a professional engineer. So he's been initially for most of these sites been signing off on them as the professional engineer on the project. like Travis mentioned, they don't exactly follow an exact standard yet. It's something that we're hoping to eventually maybe have as a standard. I don't know exactly how that would work. But for now, the cost sharing kind of has to be specialized. So for that last site that I talked about, we had a GLRI grant that was didn't have restrictions on what exactly the funding needed to be for. So we were able to put some of the funding for that into that project. And then we actually got a private donation from the fishing or from the Nature Conservancy to actually pay for a lot of the project itself. And yeah, so that's kind of where we're at with the standards and whatnot.
All right, we can go back to the chat box. What do you anticipate the life of the practice will be? Do you think productions will continue to be as high several years down the road? I believe this question came in after the first project example you gave, Wes.
Sure. So we build in to our designs approximately well, first I want to just comment on this spot right here. That spot in the field, the ditch used to overflow that road every once in a while. And after we put in this complex, this waterway that's here essentially healed itself, and that road has not had any problems with flooding, which is kind of a cool thing to just notice from putting in one of these sites. But back to that question, we build in approximately 10 years of sediment storage, supposed to be 10 years of sediment storage. What we've noticed is they're filling up a lot faster than what we were expecting. We did have some pretty wet years there for a couple of years, so we don't know if that had something to do with it. But the first site, we filled up the sediment basin in 3 years when it was supposed to take 10. So that's why on this second site and the last site that I showed, we actually have, this is kind of like a ramp to allow excavator to go in and actually clean out these traps a lot easier. And that's kind of how we're looking at it going forward. So we build in that sediment storage, but we know they're going to fill up faster unless we start doing more on the contributing watersheds.
All right.
Another
Yeah,
question.
probably got time for one more, Kelly.
All right, and I think I just got the one in the chat right now.
Yeah.
With the proven effectiveness at trapping total suspended solids and capturing phosphorus by these projects, who is the long-term party responsible for removing the accumulated sediment and vegetation so that the projects maintain their trapping efficiency?
Yeah, so that's another complication that we're trying to work through. For right now, it's the landowner that's responsible. They sign a 10-year or 15-year operations and maintenance plan. And then after that, it's kind of up to them if they want to keep the project going. So as of right now, they have the 10 or 15 years where they're responsible. If it fills up, they have to get it cleaned out. We're hoping to eventually come up with some sort of system where we can actually help pay for the maintenance aspects in perpetuity, but that's something that we don't have an exact answer on yet.
All right, sounds good. All right, thanks, Wes. Cool projects. Like Wes said, I've had the pleasure to be out on these projects, and they're pretty awesome. So thank you. All right, next we're gonna have Luke with Outagamie County. Luke's gonna be talking about two-stage ditching, two-stage channels. So Luke, if you're ready, go for it.
Yeah, can you hear me and see my presentation?
Yep, looks good. Sounds good.
All right, so let's kick it off here. So I am Luke Hickey. I also work with Outagamie County Land Conservation Department as an engineering technician. I work hand in hand with Wes. Wes was also a big part in the successful two-stage channel we did this past fall, as Travis was a part of it as well as Jeremy from our office. So shout out to those guys. So little overview of what we're going to be talking about today. So I'm going to be talking about a two-stage channel versus a traditional ditching concept. I'm going to talk about the proper location when you're looking to build a two-stage channel. I'm going to talk about the design process involved a little bit with these two-stage channel creations, a little bit of cost associated with the two-stage channels, the construction process, and I'm going to share a couple helpful tips that I learned along the way this past fall with the few that we installed. So let's talk about what exactly a two-stage is. So a two-stage channel falls under the NRCS practice 582 open channel flow. So it's going to consist of two stages, or your first stage is represented in this, the full two stages is represented in this outline in the right-hand corner of your screen, but the first stage is represented by the dashed line that also kind of represents like a traditional ditching concept. And then the second stage, or your benches, are represented by the full lines. And then you're going to side slope eventually when you're done with construction back to your existing ground. So that kind of gives you an idea of what a two-stage looks like. So now let's talk about the actual advantages of a two-stage over a traditional ditching concept. So there's a lot of really great advantages of a two-stage over a traditional ditch. I just want to put the disclaimer out there that if you're installing a two-stage, it's definitely not just a straight-out dredging project of a existing ditch. It's a conservation practice by creating a floodplain, basically. So by creating that floodplain through the two-stage process, you're also going to be encouraging natural meander and restoring that main flow channel, or the first stage, back to its historic flow characteristics. You're going to be creating the second stage, or the main part of the two-stage, and that's going to mimic a natural floodplain. And then with your second stage, or your natural floodplain, you're going to see great reduction benefits as far as nutrient reduction, phosphorus and nitrogen reductions, as well as solid sediment falling out on those benches. So this image here illustrates another great advantage of a two-stage ditch, in that if you have a lot of tiles, you can outlet those tiles onto these two-stage benches before they enter the main flow channel, and it's going to further help you with filtering out those nutrients in that water. There's some awesome maintenance advantages of these two stages, and maybe why they're going to come really popular. They're already becoming really popular in our county and the surrounding area. Those maintenance advantages are that we design the main flow channel so that sediment continues to flow through it. So we'll get into that a little later on, but basically the concept is that as a storm event occurs, you're gonna see a flushing effect in that main channel, and you're gonna flush that sediment out onto your benches. And then from there, you can go in there later on with a skid steer in the heart of summer when it's drier. Something as simple as a skid steer, if you're seeing sedimentation occurring, you can clean out those benches and you can get out of there, versus having to do a full out dredging project that we want to try to avoid. And then another maintenance advantage, and something we kind of want to promote with these two stages, is annual mowing at least once a year, keep that woody debris down, as well as promote additional nutrient uptake with those plants growing. And then of course, you're going to see good wildlife habitat by mimicking that natural floodplain. Spawning fish in the spring, as well as waterfowl, are probably going to use these two-stage benches. So let's talk a little bit of the proper location of installing a two-stage ditch. Say that you have a landowner that comes to you, as probably many of us in our counties get quite often. Landowners comes to us and say, hey, my ditch isn't draining right. What can you do for me? Well, now that you've learned this great ditching concept of a two-stage ditch, as conservationists, that's what you're going to want to do, right? So here's a couple things to consider when that landowner comes forward to you with a location of maybe putting in a two-stage. So you want to consider the watershed size, and we'll get into this a little bit later on in the design process, but the watershed size is really important because you're going to want to find that happy medium. If you're designing in a watershed that's just way too big, it's just not going to be feasible or cost efficient to build these two stages, and you're probably not going to have enough area to build your benches. And if you're in a watershed that's too small, it's just also not going to make much sense to build this two-stage concept, because you're just not going to have big enough benches to see any of those reductions. And that watershed size is they recommend in the standard 1 to 10 square miles. A two-stage would fit in that category pretty well. So it gives you a lot of playroom there. Accessibility of your two-stage site location is very important to consider. That's going to directly influence your cost. We'll talk about that a little later on. But also with accessibility comes something like wetlands. So if you see here in this photo, I have the hydric soils later on the DNR website. That's something to pay attention to when looking at these locations originally. Make sure you note of any wetlands and the hydric soils in the area. That's gonna, you're gonna want to stay out of those areas, and especially when you're doing building your benches and taking any material out, you can't spread those spoils into those hydric soils. So that's something to make sure that you can go close by and spread your spoils. Otherwise, it's gonna really bump up your costs. Another thing it kind of plays hand in hand with your watershed size is the reductions you're gonna get off of your two-stage when you're looking at a location. Once again, kind of goes back to that happy medium. Finding the perfect two-stage location is going to obviously give you the best reductions. And then something to consider is the permitting process for these two stages. So we actually try to get by with most of our two stages with a general permit, because we're doing very minimal main channel excavation unless we have a lot of sedimentation occurring there. So that allows you 25 cubic yards or less of in-channel excavation per landowner involved. Otherwise, if you do have a lot of sedimentation, which is probably also a possibility because, that's probably why the landowner's coming to you in the first place, you're gonna need to go the individual permit route, and just know that's gonna be probably a minimal of 3 months to get that permit through. And then also just make sure you pay attention to any county or township permits. I'm sure you know what you're gonna need depending on what county you're in. All right, so let's get into the design a little bit. So the initial first step is to go out and walk your site and take a survey. So I like to take a really thorough survey to start versus using all LiDAR data on these ditches. That's the most accurate way to do this. So that's gonna contain going out and shooting a lot of centerline shots. Shoot all your inverts so you can set grade later on in your profile. You're going to want to shoot a lot of cross sections to give you a really good idea of what kind of cut you're going to be taking when you're building your benches. And then also shoot sediment layers throughout, or sediment levels throughout your ditch. So in our county, we run all GPS grade survey equipment when possible. So for us, that just means we simply take a shot at the top of the sediment, soft sediment, and then we'll push that probe down until we hit the hard bottom. And then when you bring that back into your design process and throw that into AutoCAD, you can see the difference in sedimentation. It gives you a really good idea of how much sediment you'll be having to take out, and that's going to directly influence maybe what kind of permit you go after for your two-stage project. And then I mentioned LiDAR. So once I get all this survey information done, then I'll combine that with my LiDAR data, and that will give you a really good idea of everything going on in the area as far as elevations. So continuing on with the design process, we talked a little bit about the importance of delineating your watershed, but how exactly do you do that? So Wes mentioned Presto report in his presentation. I also rely heavily on a Presto report, or you could use the GIS delineation tool. Both work great. If you're GIS whiz, the GIS delineation tool is probably the best choice. It's more accurate, we found, in the Presto reports. But what we have found with the Presto report is it seems to err on the side of a bigger watershed, which is okay if we're, as engineers, we want to over design things, especially in the case of a practice like this. So once you figure out your watershed size, you delineate your watershed, and then you're going to want to throw that into your flood frequency spreadsheet. Just like what Wes mentioned, flood frequency spreadsheets in his presentation, they are very important for two-stage designs as well. So here you can see that like a 1 year, 2 year, 5 year, 10-year storm are all represented there. And it gives you your different velocities that you're going to be seeing with those storm events. So once you have your flood frequency spreadsheet filled out, the next step is to put that into your two-stage design spreadsheet. And this is really where you get into the heart of your design, and it's going to determine what your two-stage is going to look like as a final result. So the main thing here is that you put in all your variables in red properly. Your Manning's coefficient is very important that you put the correct one in there. Your width of your first stage. And I should mention right now, we're just looking at your first stage design. So you're going to put in your grade, your depth of your main flow channel, and the side slope that you're going to have up to your benches. So we design our main first stage of our 2-stage ditch to withhold a half-year storm event. And then after a half-year storm event, it will start to flood out onto your benches. So as you can see, the capacity of this ditch is just over 10 cubic feet per second. And our half-year storm event was 10 cubic feet per second. So we're holding that half-year storm event. Another really important thing to note here is just above capacity on that spreadsheet is the velocity at 2.2. We want to keep that velocity, and I mentioned this earlier about how the sediment, we want to flush it out. We want to keep that velocity at 2 as a minimum, to about 6 feet per second at a very maximum. Keeping it above 2 will allow for those particles to keep moving, and that's going to be really important so you don't see sedimentation in that ditch in the main flow channel, and then that's going to push those particles out into your benches, and that's where you're going to retain them and keep them out of the water. And then if you go over 6 with your velocity, you're going to start to run into erosion issues. So once you have your first stage designed to withhold your half-year storm event, you're going to want to go into your second stage or designing your benches. So here's the rest of that spreadsheet. So those benches are going to hold a 1 to 2 year storm event. We designed this to withhold a 2-year storm event. And like I said a couple of times now, those benches are mimicking a natural floodplain. So if you look at the highlighted capacity of this ditch that we did this past fall, it falls within that flood frequency spreadsheet of a 2-year, 24-hour storm event. It's really important to have that conversation with your landowners that that the final product is going to withhold a 24-hour storm event. So just during a storm event, you're going to have just over 2.5 inches of rainfall, and that's going to be withheld within those banks. Whereas if you have like a 12-hour storm event, that still may not be withheld within those banks just because it's more of a gully gusher effect. So make sure you have that conversation that it's for a 24-hour storm event, over that 24-hour period. Just some other important things to note on your second stage. Once again, you're going to play around a little bit with your widths to fit your site. You're going to put in your Manning's coefficient again, your side slopes back to existing ground, and then different depths of that bench up to the final ground that you're going to grade up to. And then once again, make sure your velocities fall between that 2 and 6 feet per second of velocity. All right, so just a little bit about how I go about creating a good construction plan to make it not confusing for your contractors. So just stick to the basics. Don't try to make things too complicated. So you're going to want a good plan view, some good cross sections, and then you're also going to want to have really good quantities. Those quantities are going to directly influence your first bid you get on that job, obviously. And then don't be afraid to be creative. So this image in the bottom right-hand corner illustrates that we were a little creative in this section of 2-stage. And the fact that our first stage or our main flow channel actually ran into the township easement and ran in the township ditch for a little bit. And we didn't have the space or the permits to kind of go in there and keep working on our benches. So what we did is we continued our natural floodplain as an overflow channel here to still get that those benches and that good natural floodplain effect as the main channel continued straight there, and then it adjoined later on. So just don't be afraid to be creative. Every site's going to be a little different. All right, so let's talk a little bit about costs involved in a 2-stage. So you're going to have a lot of things that are going to influence your cost. We talked a lot about location already, and to just make sure that you're considering hauling, staying out of those hydric soils and wetlands with your spoils is really important. If you have to haul half a mile or even more down the road, a couple miles down the road, that's really going to hike up your cost of your job quickly. Versus the best case scenario is you're going to have your excavator. He's going to cut out those benches. He'll throw them into the adjacent field as long as it's out of hydric soils. And the guys can just push it out to grade with the bulldozer. That's going to be your lowest cost scenario. Weather, another thing, obviously we've all probably dealt with weather throwing us curveballs with these jobs, but this middle picture illustrates how we didn't originally plan for it and cost for this big site truck. I think this was a 30 cubic yard site truck to be on site. He was just going to use his dump trucks, but he had to bring this in to move some of the ground because we received 2 inches of rainfall, and he just couldn't get in there with his dump trucks. Of course, we received 2 inches of rainfall right as the job starts. It always seems to happen for us. So a little bit about breaking this down to a linear footage cost. So obviously a contractor charges per cubic yard, but for a lot of estimate purposes, such as EQIP, you can get EQIP NRCS funding for these 2 stages, but that gives you a linear footage payment. So it's really hard to put an actual value on how much a 2-stage is going to cost per linear footage. For example, we did 3 sections this past fall, and one section came out to like $13 a linear foot, and another section came out to $28 a linear foot. If you look at the image in the bottom right corner of the screen, that bank on the left had a lot of cuts, so that was the really expensive area if you break it down into linear footage. So on average, that our 3 sections came out to about $20 linear foot, but something to kind of pay attention to. You can use $20 a linear foot if you're estimating, just to give you a lot of buffer. And then the image in the left-hand corner shows one of the areas of the project before construction. Obviously, there's a lot of clear and grub there, so just pay attention to that. That's going to hike up your costs as well. And then in-kind labor, that's something that we offer at our county for a lot of our jobs, so that landowners can help pitch in without having to pay. So our landowners all participated in this project by laying all the erosion matting and doing all the seeding, and one landowner ended up not having to pay anything except for some of the materials and seed. So that's a great option if you can do that in your counties for landowners to get involved and cut down on their costs. All right, so let's get into the actual construction process, my favorite part of the whole deal. So the first thing you want to do, you're probably going to have to do a lot of clear and grub in these sites, so get your contractor in there to do that. As soon as they're done, go in and stake out. So this is going to act as a really good guide for your contractors, and it's really important to stake out that center line really well, and to make sure that that center line can mimic the natural stream meander and encourage natural stream meander when possible. So the next step after you get everything staked out is to restore your main flow channel first. And setting correct grade is really important in that main flow channel, because the rest of your design is kind of based off of that elevation that you set for your main flow channel. So say you have your benches set 1 foot above your main flow channel, you're going to want to always have that going throughout your job. So really don't be afraid to get dirty. I got right in the stream with the contractor with the GPS and was checking grade the whole time to make sure that our grades are right in our main flow channel. One tip we learned was for the main flow channel, do that first and start downstream and work up. I know it kind of goes against conventional stream work, and you should work upstream and work down, but for us, what we had to do is we had to start on the downstream end and work up, because we had a rain event right before we started construction, and our benches were actually flooding out that we had designed for. So we knew the water would drop eventually, so we didn't want to raise our bench elevations. So we worked from downstream going up, and that actually helped the whole system drain a little faster and a little better. And then from there, we put on our benches. And then once you start building your benches, you can start from the upstream side and work down. So that was just a helpful tip. Otherwise, you're going to run into a muddy mess of your benches flooding out, which is what we ran into originally. All right. So continuing with the construction process, next thing you do once you get your main channel or your first stage all cut to grade, cut in your benches. So you're going to have everything staked out But don't be afraid to go out there with your survey equipment and your GPS and get that first bench on one side all set to grade properly. And then from there, the contractor can set up his laser level and he can just match grade on that other bench once he goes to the other side. Another thing to note when you're cutting in your benches is, say you have a 10-foot width of benches on both sides of your stream, you don't necessarily need to keep a 10-foot bench on each side. We want to really promote the natural meander of that stream and restore it to its more natural means. So if you do like 15 feet of bench on one side and 5 on the other, with a natural meander through the middle, that's fine, as long as you're getting that final width, you know, adding up right. And then just a reminder on all of our projects, not just two-stage, communication is key with our contractors. They all do really good work for the most part, but just being available when they need to talk to you is important for the success of the project. So don't forget your erosion control. I put this slide in here because I didn't know about the matting when I first started this project. The Wisconsin DOT Class 1 Type B erosion matting is what you want. The Class 1 stands for the organic material versus like the plastic material. You don't want that in any stream project. So you want to get that Class 1 organic material. And the Type B stands for double netted material. That's going to withstand high velocities that you're going to see after storm events going through these projects. And then don't forget to seed and mulch. The image on the bottom right shows that we mulched the area that was not under the matting at the best we could. Work with your agronomist for the best seed mix. I'd recommend any seed mix that comes up well in very wet places. So if there's any questions, I can take some questions now. Here's my contact information. Otherwise, if you do start building a two-stage down the road, feel free to reach out to me, and we will get you everything that I can to help you out. And while we're taking questions, I'm going to try to play a drone video as well, like Wes did, of one of the sites. So can you see the drone video?
Yep.
All right.
One question in the chat right now. The two-stage channels are for only perennial streams? That's a question. Or intermittent also?
Yeah, they're gonna fit more into in a smaller stream. Like I said, it's gonna be based on your watershed size. It's gotta fit between 1 and 10 square miles. So.
No other questions in the chat right now.
All right. Yeah, I guess we got about 5 or 7 minutes before we're done. So I guess if anybody does have a question from our previous two presenters as well, we could address those at this time as well. So
Travis, the other thing I wanted to mention with the drone video here is that this promotes that natural meander that I was talking about. You can really see how we didn't stick to one width on the banks. It kind of went back and forth.
Yep. Yeah, I'm glad you brought that up, because that was, you had that on several of your projects. Don't get stuck in it's got to be the same on both sides. That's a good thing to keep in mind. So
we're getting a few more questions. Somebody wants to know who flies your drone?
Wes flew the drone. Wes is certified. I'm working on mine, but if it looks really bad, you can blame it on Wes.
What are you using for design of the natural meander? Rosgan?
The natural meander, so in this case of the drone video, it was kind of there already. So we just worked with our contractor on site to make sure that they follow that natural meander versus just straight lining it.
In a site, I'm going to step in there. In a site where it is a straight line channel, you may want to throw in some meanders, and you could use the Rosgan channel design for that.
And that addresses the other question we had in the chat box as well. So
yeah, the other things with these is they'll kind of, even if it is a straight line, eventually, you know, it's going to happen naturally. If you give it a floodplain, the stream's going to eventually start moving. So you will see those natural meanders start showing up in that floodplain.